by popular request. 4.2 number 9 is what we're going to talk about right here. And this is typical of conservation of momentum problems where straight conservation of momentum by itself is not that elaborate. You got one or two things, colliding or exploding and turning into one or two things. And so, you've got your MVs of the objects before and after, which is relatively straightforward. But in many cases, that situation is going to be surrounded by some more elaborate scenario. And some combination of projectiles where things are being launched and then they explode, or things are being launched and then they collide, or things are being dropped or fired upward or downward, or things collide and then they swing up or they swing down. Some combination of actions around the collision itself, which makes the problem more elaborate and more involved to solve it. And so number 9 is very much like that. It says a 75 kilogram shell is fired with an initial speed of 125 meters per second at an angle of 55 degrees above the horizontal. So it's going to see 55 degrees. Just draw a little diagram to give us something to look at. 55 degrees, a little bit steeper than halfway. So angle is 55 degrees. At its highest point, the shell explodes into 2 fragments. So it's going to, as projectiles do, follow this arcing path, except at this point right there, at the high point, it explodes into 2 fragments, one 4 times as massive as the other. The heavier fragment lands just below the point of explosion. So we've got the big piece is going to just drop straight down, and the little piece is going to go way over there somewhere. The heavier fragment lands just below the point of explosion if the explosion exerts only horizontal forces. So at this highest point, neither piece is being launched upward nor downward. Only horizontal forces are exerted. How far from the launch point does the lighter fragment land? All right. Anything else we need to know? I guess we'll assume, since we're not told otherwise, that the ground continues indefinitely. So it's launched and lands at the same height. So we've got to do a few things. We've got to figure out where this highest point is and what's going on there. Maybe what is its velocity at that highest point. We're told that there are 2 fragments, and we are given some information about the masses of each piece. We're given information about the total mass, so that's good. And we're given its initial speed. So, all right, let's start with the projectile side of things. So we'll find out what's going on at the top or the peak of its travel. So if we treat this like a projectile, we've got VOY and VX, its original Y velocity, since it was launched at 125 meters per second at an angle of 55. That's going to be 125 times sine of 55 degrees. And the X velocity is going to be 125 times the cos of 55 degrees. So 125 sine 55 gives 102.4 meters per second vertical launch velocity, and 125 cos 55 is 71.7 meters per second horizontal velocity. All right, there's a couple things that this tells us. One, at the peak, the velocity of this mass is exclusively the x velocity, because that's what makes it the peak. It's not going up, it's not going down. So at the peak, its velocity in the y direction is 0. So we know its velocity at the top of the arc. It'd be good to know something about the air time, because this heavier shell, the larger shell, is falling straight below the point of explosion with no y velocity. So it's basically, as the pieces burst apart, there's enough forward push on the smaller piece to stop the bigger piece in its tracks. So they're both moving up together, and the smaller piece goes flying fast, the larger piece is stopped, and then just plummets straight down. So we treat that just like a falling object due to gravity. So we'd like to know something about its height, and thus the air time, the time that it's going to be in, that it has to fall. So that's when its y velocity is going to run out. So if we use that to find its height, say that vfy squared equals voy squared plus 2ad. Do we care about the distance? Might just be interested in the time, and that's all we need to know. Yeah, we really only need to know about the time. So VF equals VO y plus AT. All right, so VFY is 0, VOY is 102.4 plus acceleration, which is gravity, so that's going to be negative 10 times t. So 102.4 divided by 10 is going to be negative 102.4 over negative 10 is the time. It's going to be 10.24 seconds of air time. All right. So that means the small piece is also going to have 10.24 seconds of air time as it falls and moves horizontally. So to know how far it launches or how far it goes from the launch point, all right, well, we're going to have to actually break this whole process into two pieces. We got the from launch up until explosion, and then we got from the explosion until sometime later when the small piece lands. We'll have to solve those separately. Well, the first part is kind of easy. We already have the time. It takes 10.24 seconds to go up and also 10.24 seconds to go down. So the 10.24 seconds on its way up, it's going to be traveling horizontally some displacement in the x direction. That's going to be Vx times the time. So that's going to be 71.7 times 10.24. So the displacement in the x direction is going to be times 10.24 is 734 point roughly 2 meters. All right. So that's just dx right there. Just that segment. We haven't dealt with the explosion or the after the explosion yet. Well, to find out the distance that the smaller piece travels horizontally, we've got to know what its velocity is horizontally now. So here's where we deal with the momentum. Conservation of momentum. So initially, let's only deal with the horizontal velocity because that's the only velocity that, because at the peak, that's all it has. So we've got m total times v is going to turn into m1 v1 prime plus m2 v2 prime. So the mass total, the total mass is 75 kilograms. And its velocity was, in the x direction, 71.7. And what's going to become of that is the larger piece is going to have no momentum after the explosion. It's stopped dead in its tracks, horizontally anyway. And so that means the small mass is going to get all of the momentum. But we need to know what the mass is of each of those. Well, we were told that it's going to be a ratio of 4 to 1. So if we break 75 kilograms into a 4 to 1 ratio, that's like 80-20. So 20% of 75 is 15 kilograms. I'm just saying that out loud because we can deal with 4 to 1 of 75 kilograms is going to be 60 and 15, just proportions. So we're talking about the 15 kilogram portion. So we've got a 15 kilogram piece going at some velocity horizontally. So 75 times 71.7 divided by 15 tells us it's going 358.5 meters per second. All right, so we need that because now this piece is, we've just found V2 prime. It's going 358.5 meters per second, and it has 10.24 seconds of travel before it hits the ground. So its displacement, called dx prime after the explosion, is going to be its velocity. I guess we'll refer to the variables that we already have, v2 prime times t. So that's going to be 358.5 times 10.24 seconds. That's going to be 3,671 meters. And that is dx prime just from there. From there to there. So we add those two together and we get the total distance that it travels from launch plus 734.2, 4405. D total, it's going to be both of those together, dx plus dx prime. It would be 4405.24 meters. That little decimal, kind of irrelevant. It's a large number. It's a little bit of rounding. So, like we said, sure, conservation of momentum is in there, but it's like 1/5 of the entire problem because the whole scenario built up around the explosion or the collision. And that's generally how these kind of things go. Hope it helped.